We will continue our discussion on the electroweak interactions, understanding it through the gauge transformations. So, we said that we had to consider a gauge symmetry with the group SU2 L cross U1 Y, where L denotes that fact that only the left-handed particles are charged under SU2 and Y denotes that there is a charge called hypercharge, which dictates the interaction or transformation through U1. And psi L left-handed particles transforms like psi L prime equal to e power I theta a plus I alpha y. Earlier we had denoted this hypercharge parameter along with the hypercharge as phi, but for reasons that will be clear as we go on, we will denote it by alpha now. Reason is that later on we will consider the scalar field, where we will usually denote that by the standard notation phi, and we do not want to confuse you with this thing. So, we will change the notation here compared to the earlier this one. This L A is equal to 1, 2, 3, y is whatever the hypercharge is, and essentially for infinitesimal transformation, we write this is a doublet. For doublets, I mean for usually all the particles, leptons and quarks that has a non-zero SU2 charge is isospin is taken in a doublet of SU isospin equal to 1 by 2. So, let us say nu EL corresponding fields, the primed version of this is equal to 1 plus I theta a I a plus I alpha y, sorry here y by 2 is there, y by 2. Again there is 1 over 2 for y is a convention. This times acting on nu EL. I A is 2 by 2 matrix. The first term and the last term, there is no 2 by 2 matrix, but we will assume that there is a unit 2 by 2 matrix. Okay. And in particular, I can be written as I1 as the Pauli matrix by 2 0 1 1 0, I2 is equal to the second Pauli matrix sigma 2 minus I0 again 1 over 2, and I3 equal to 1 over 2 1 0 0 minus 1, and this factor of 1 over 2 on y is mainly due to this thing. So, this is the way it is, and the right handed field transforms as 1 plus I alpha y by 2 ER, no isospin, isospin is equal to 0 for this thing. Now, let us look at the Lagrangian. Let us only look at the electron part. So, we have I nu EL bar gamma mu d mu acting on nu EL, nu EL, EL, this is 1 and this is a d mu which act on the left handed doublet. For the right handed field, I have I E r bar gamma mu d mu r E r. D mu L is dou mu plus I g I a w mu a I g prime y by 2 b mu. So, we have introduced 3 w mu's and 1 b mu. So, total 4 bosons, vector particles, vector fields here, and they are the ones which help us have the gauge invariance for the Lagrangians. For the right handed particles, the transformation is with the covariant derivative dou mu plus I g prime y by 2 b mu, and this is because I is equal to 0 for this particle. Now, we said how the size transform here, then W's transform like W mu A goes to W mu A prime equal to W mu A 1 over g derivative of theta A epsilon A B C theta B W mu C. B mu goes to B mu prime equal to B mu minus 1 over G prime dou mu alpha. So, this is familiar to us. SU2W, the gauge bosons that correspond to the SU2 transformation W mu is transform in a similar way compared to the G mu's we introduced in the case of SU3, the gluon fields. Whereas, B mu which correspond to a U1 gauge transformation transform similar to the A mu which we had in the electromagnetic transformation. So, we will not spend too much time dwelling on this because we are familiar with these things. Now, let me write down the Lagrangian I psi L bar gamma mu d mu L psi L plus I psi r bar gamma mu d mu r psi r. This is what we had written down earlier as well. This is gauge invariant now, but now to make the newly introduced particle physical particles, we need to add the kinetic energy term. So, it is the usual notation that we consider 1 over minus 1 over 4 W mu nu A W mu nu A minus 1 over 4 B mu nu B mu nu, where W mu nu A is defined in an exactly similar way as G mu nu, dou mu W nu, dou nu W mu, and a non-abelian term G epsilon A B C W mu B W nu C. Whereas, B mu nu correspond to the U1 and it will be exactly similar to F mu nu, dou mu B nu minus dou nu B mu. There is nothing, no third term, and we have only one B. So, we cannot make any antisymmetric combination with one particular component object. So, this is the Lagrangian which is invariant under SU2 cross U1 and everything seems to be fine. What is missing? There is something missing here. The kinetic energy term is there, no problem, and there are interaction terms through this d mu. D mu L has both B mu and W mu in it. So, there are interactions of the left-handed particles with both W's and B. Right-handed particles in the second term of the Lagrangian has d mu r, which has only B mu in it apart from the normal derivative. So, right-handed particles interact with B, not with the W's. But what is missing is the mass term. Where are the mass terms? We had written down the mass term both in the case of electromagnetic interaction and QCD, the strong interaction, quantum chromodynamics, whereas in this case we do not write down that this thing. Nature of SU2 group leads to, or this cannot be said either way, I A I B equal to I epsilon A B C I C. So, these are again called the structure constants, that is what we had used, and looking at the W mu nu, very similar to the G mu nu A, we have here again self interaction of the W's. So, this leads to self interaction of the W gauge bosons, both triple interaction and quartic interactions. This is proportional to the G, the coupling constant, and this is proportional to G square. Okay. In addition to the interaction with fermions, W's all have these interactions, whereas the B do not have any self interactions. It is similar to the photon. Let us look at the mass term. We know that electron has mass. So, are the quarks and muons and tau particles. Neutrino do not have mass, okay, fine, within the standard model, and then it has a tiny mass experimentally determined, which we will come to in a different way later on, which will have to be analyzed in a completely different way. Let us focus on the masses of the other particles, the electrons, all the charged leptons, electron, muon and tau lepton, and all the quarks. They are found to be massive, and then how do we generate mass? Firstly, why couldn't we write a mass term in the earlier Lagrangian? Let us see how to write a mass term. L mass, what do? I have to have a term psi L m psi L. Why should I club this with this psi L with psi L? It is because that is the only way to do it. with a gauge invariance, with gauge SU2 gauge invariance, because psi L transform in a way which will be cancelled by psi L bar. Okay. So, this is fine, but the other, okay, let me write down the other this thing you can have. So, okay, let me call this ML psi bar R M R psi R. M are some coefficients, it could be a matrix, it could not be a matrix. In the first it could be a 2 by 2 matrix, in the second it need not to be a, it cannot be a matrix, anyway there is only one term. Plus you can also have, if you want, psi bar L M psi R and the Hermitian conjugate of this thing, plus Hermitian conjugate if you want. Now, problem with this terms are the following. Let me start with the last term. So, the third term psi L bar M psi R is not or cannot be made SU2 L cross U1 Y invariant. Actually, problem is with SU2 L invariance. That is because the doublet transforms in a particular way, including the SU2 part, and right handed wave function field transform without including any isospin part in that this thing. So, this will not be conserved, there is no way to cancel that from the phase factors from of psi R and psi L bar. What about the other term? Let us look at first psi R bar M R. So, let me write it as M R psi R. This is equal to whatever M is psi bar 1 minus gamma 5 by 2 1 plus gamma 5 by 2 psi, for psi R is equal to 1 plus gamma 5 by 2 psi and psi L is equal to 1 minus gamma 5 by 2 psi. Okay. So, this is equal to M R by 4 psi bar 1 minus gamma 5 plus gamma 5 minus gamma 5 square psi. Gamma 5 square is equal to 1. That makes this psi R bar psi R equal to 0 for any psi. This is equal to 0. So, we cannot have an interaction like this, a term like this possible. Similarly, psi L bar psi L is also equal to 0. So, that tells you that Lagrangian mass term is equal to 0. You cannot have, for if you want consistent with SU2 symmetry. What does this mean? This means that only possibility. So, in this Lagrangian here, only possibility is to have third term. First two terms are not possible technically, I mean it It is just a question of, I mean, they are identically vanished. There is nothing to do with gauge invariance or anything. They are gauge invariant, of course, but reason for that to be 0 is to do with the way the projections are multiplied. Now, the third term is the only hope for us, but we do not have gauge invariance for that. Actually, that is something which we have to live with. Okay? We need to break SU2 symmetry or SU2 cross U1 symmetry. In order to have mass term for the Lagrangian. This is for the fermions. Even for the gauge bosons, we have added interaction term for the various things, including psi bar, gamma mu, d mu L psi L. Interaction is added through this d, and we have added 1/4 W mu nu A, W mu nu. Kinetic energy term for this and self interaction term. But the self interaction term always had 3 W's or 4 W's in it. And wherever you had 2 W's, let us go back to that here. When you have W mu nu term, either you have 3 terms, 3 W's with 1 derivative acting on one of those, or we have 4 W's. Where we had 2 W's, we had 2 derivatives acting on it, which is actually the kinetic energy term. There is no mass term. The mass term for the gauge boson is essentially one which is equal to something, some constant into W mu W mu. This is the kind of term that will give you the mass. Square in this. How do I justify this? All right. So, let us look at the Lagrangian. Dou mu W minus 1/4 F mu nu F mu nu. For simplicity, we will take a non-abelian kind of this thing, okay, minus, or let us take a B mu nu, which is immediately familiar to us. M square M B square B mu B mu. What is the equation of motion? So, what this part is purely derivative term. The first term has only derivative terms. So, that will give you dou L over dou B mu is equal to, because of the symmetry, minus 2 M B square B mu. Okay. And dou L by, you write down the equation of motion for this, that will give you the equation of motion del square B mu box square mu B mu minus minus of minus plus m b square B mu equal to 0. So, the mass term in the Lagrangian is similar to the mass term for the phi, the Klein-Gordon equation part. Okay, these are all Klein-Gordon thing. Okay, so this is for there is part of this thing is there, then there is also term minus dou mu dou nu B nu. Okay. So, this gives you, this tells you that the mass term is similar to this. But now, if you focus on that, on the mass term, you see that this is not invariant under gauge transformation, where B mu goes to B mu minus 1 over G dou mu alpha and B mu 1 over G dou mu alpha. This is not equal to B mu B mu. It is not possible to have these things. So, this is the reason why we cannot have mass term for the gauge bosons as well. Therefore, that leads to mass terms for B mu, W mu or G mu will not be gauge invariant. So, there are two issues. One is to generate the gauge boson, the fermion or the particle, normal particle masses. Other is to introduce masses for the gauge bosons. We will see later on that the gauge, why should we have the gauge boson mass? We will see that the photon is massless anyway, and then the gluons are also massless, but we will see that weak gauge bosons are massive. Weak gauge bosons are massive. We have determined the mass of this experimentally. We have discovered these particles, and then we have seen that they have mass. That is one thing, but the other thing is that it was expected that they are massive, because they they correspond to the weak nuclear interactions which are short range. And for short range particle interactions, the exchange particle is expected to have mass. Otherwise, the range of the interaction will be infinite, like the electromagnetic interaction. It is a different story why strong interactions are short range even with gluon as the exchange particle without any mass. That we will not consider for the time being. And we saw also that SU2L cross U1Y cannot be an exact symmetry. because there are masses for all these particles, and then to generate the mass for this particle we need to break the theory, okay, break the gauge invariance. So, we cannot add any mass term explicitly to the Lagrangian and break the symmetry. Breaking the symmetry explicitly. By explicit we mean by adding mass terms to the Lagrangian. This is not a good idea, because this leads to various problems. Okay. So, in order to avoid all this problem, is there a way out? Way out is what is called spontaneous symmetry breaking.